All right, so galaxy evolution, most of the other surveys or projects are organized around a central theme or a central facility or a survey or something. That is not the way galaxy evolution works. It's a number of sort of medium-sized projects. And I want to go back to one of my favorite plots that ever gets made because it's just fun to look at, and it actually makes sense as listers, I don't know, spaghetti diagram or whatever you want to call it. And galaxy evolution is the largest theme, and we publish a lot, but half of our stuff is collaborative. And that is a theme I'm going to hit multiple times throughout this talk. This is basically an overview of overview talks, and so I'm really going to kind of talk more about how we do things. So XQR30 is a VLT large program using XShooter, and the people at Swinburne are doing a significant fraction of work. That's largely Emma Ryan Weber, who we just heard from. Her group leads this, and Rebecca Davies, postdoc at Swinburne, has produced the catalog of something like 800 absorbers systems. And so this will be a definitive catalog that is used by many people, and so it's a real big, significant contribution to that field that Rebecca has made for that team. And you can use it for science. Rebecca's doing science with it, but the students at Swinburne, Alma Sebastian and Stephanie Rowlands, what they're doing is they're using the line ratios and the evolution of the emission lines from these to learn about things like the UVB. And so Alma's work, it uses the metal lines and looks at the redshift evolution of them. That's what you see here on this side. And what you see is the lines do not decay over time. And we know that metallicity is decreasing as you go back further in the redshift, which means the UV background, the thing that ionizes the lines in absorber systems, must be changing. Stephanie Rowlands is using line ratios, coming to a similar conclusion. So you can use the different lines and you can peel out the shape of the ionizing source, which is your background emission. And she finds basically the same thing, that the UVB needs to be changing as you go to higher redshift. So the Duvet project is a project I lead, and there's going to be too many talks on Duvet later today, and Bron is going to give a really nice overview. I just want to sort of point out the context of what this project is. So by and large, it's a Keck project, about 10 nights, studying outflows in a resolved sense. And we know a lot about hyper-resolved outflows from like NGC 253, and we know a lot about unresolved outflows, but that mid-range is rife and is open for discovery space. And this is an example of working with Alex Cameron, who wasn't even a Duvet member. And we looked into the data cubes, and we realized we're able to measure the metallicity of the outflow. And so this is quite complicated for technical reasons, but basically you need aurora lines, and Alex found them there. And so this is what you're seeing here on your left. And you see an image of the metallicity of an edge-on galaxy. And it's a thin disk, and so when you're moving off, you're seeing the outflow. And you go to the major axis, you're seeing the inflow. So what you're looking at is low metallicity gas going into the galaxy and high metallicity gas going out. This is the first image of the baryon cycle that anybody has ever seen. And this was not in any Duvet proposal. It was not anything we ever expected to do. But it basically opens up a whole new area of study within the field, and it initiated a whole new PhD project and will become new science. So it's a fun thing to work on that we expect to see more results in the future. Ooh, excuse me, lunch. The AGIL project is impossible to keep up with. These people get too much time on too many telescopes. I can't summarize what they do. So it started out, it's a real success of collaboration within ASTRO 3D because the former head of Galaxy Evolution basically wrapped up everybody in a room and said, we're going to do a project, what is it? And at the same time, Carl Glazebrook and his group was generating machine learning techniques for finding lenses. So the fundamental problem of studying lenses is not the modeling. That's not the hard part. The hard part is that lenses are so rare, it's very difficult to build a sample. So it's very difficult to interpret your results. But Carl and Colin Jacobs were finding hundreds of candidate lenses. And so the AGIL team did the hard work of following them up with redshift surveys to make sure they're truly lens galaxies. And now they're doing the modeling. And they had a publication last year, was their survey paper, and now they're sort of moving into that next phase of producing science. And so they're looking at ways they can use it. They also recently had They had an HST snapshot program with 70 lenses. They recently had a gap filler program that can get as many as 500 lenses. So it's going to be a huge data set for the community. We had a strategy meeting in Singapore. I recommend all your strategy meetings be in Singapore. It's quite nice. Where we were talking about how to use AGIL to study cold gas, CO and dust in galaxies. And it's a real niche because we basically know nothing about how much cold gas is in low mass galaxies beyond redshift 1, because they're very difficult to find. And lenses become a way you can boost your signal and make observations. And so, it doesn't show up. So we had a program, successful program with Noema, led by Melanie Kassanen, who's an ESO fellow, to do the first ever sample of galaxies that are low mass, optically selected, so you know what the galaxy is like. Also, separate from that, Tanya Baroni is doing really interesting work of using the lenses as sources to study the CGM through absorption. So there's just a real variety of things going on in this group, and it sort of spans across many aspects of galaxy evolution. So I want to now talk about 3 separate surveys that are all using Muse on VLT. They're all large programs. Together, MAGPIE, MOVE, and GECKOS represents over 800 hours on UT4 and VLT. That is what success looks like. That is amazing. And the cohort of people running this is great. It's a lot of young people. Generally, the proposals were put in by postdocs and who moved into faculty positions. So it's a real success story overall. They sit somewhat differently within ASTRO 3D. MAGPIE was proposed originally by the ESO Fellows several years ago and has been with us throughout a lot of the center. Whereas these others will really be something that goes beyond the center, and they will start producing data once the center is done. And so the way it sort of relates to ASTRO 3D science is quite different. We'll talk about that. So this is a really awesome picture that I'm sure Trevor's going to show again. It is, I think, 40 plus fields with of the MAGPIE observations. You have high mass galaxies at the top and redder, high mass halos, sorry, at the top, and redder systems over on the right. And what you take away from this is a visual snapshot of diversity in the systems. And that's really what the MAGPIE survey is intended to do. It's going to have a powerful legacy because of it's the first survey that really sits in the sort of mid-range redshift between 0.3 and 0.5. And so it'll end up basically on every single redshift evolution plot, which is great for it. But then within it, they're basically going to know everything you want to know about how cluster evolution and how group evolution works at that redshift. In terms of collaboration, this is a story we all know well. I've talked about it many times before, but I think it's a great story. The original MAGPIE PIs included both Claudia Lagos, who comes from the genesis or simulation side of ASTRO 3D, with observers. And from the start, they wanted to have a system where both of those things evolve together and work together. And so they developed SEMSPIN, which is what Kate Harbone, who I'm sure we'll be talking about. And in that sense, it became sort of something that was as large as the survey itself. And it's now this tool that you can use to ingest different simulations and put out something that looks like IFS observations. And so together they become more than the sum of their parts. And it's a really good example of cross-theme collaboration. GECKOS was accepted last year. It is a survey of edge-on galaxies in the local universe with hyper-deep observations, as many as 10 or 15 OBs on individual pointings, with multiple pointings per galaxy. And what you see in the middle, this is one galaxy, and you see sort of absorption line diagnostics, velocity dispersion, and metallicity in the middle, and then you see H alpha. And so on the same data set, we'll be understanding details of how things like the thick disk stellar populations are working, as we will also be, at the same point, measuring outflows. And it really, GECKOS, I think, scientifically, really comes out of a lot of the science of ASTRO 3D. We've had 10 years of massively successful large IFS programs like Khalifa and SAMI and Manga But the nature of those programs leaves certain questions out, and those questions became more and more important. Off the plane, how thick systems are became much more important, and so GECKOS is directly addressing that. And I think it will have it's a very unique system. There's not been an edge-on program to this depth. But also, GECKOS brings together people from across ASTRO 3D. So these are all people who ended up on the leadership team of GECKOS. And so you have people who have their background working in SAMI and doing IFS surveys. You have people like Michael Hayden, who's working on the Milky Way and comes with that perspective. And then you have myself working with outflows on Duvet. And we all came together to successfully propose for one of the largest MUSE programs that has been accepted. And there you have, we added Marie Martin. She was not an ASTRO. And MOVE, I'm not going to discuss anything scientifically because I don't want to take anything away from Luca and Barbara. This is the science of it is a multi-wavelength study of the Virgo cluster, and it really is their expertise. But when it comes to collaboration and how that's working within ASTRO 3D, it's really different than the way other surveys. So we were both successful with MUSE at the same time, and it would be totally reasonable for us to say, we're just friendly competitors. You guys do what you all want to do. We're going to do what we're doing. But we didn't do that. It's a very close-knit collaboration. We're developing data reduction pipelines and analysis pipelines together. And we're creating different modules together because we both want each other to be successful. And I think that's an attitude of collaboration. While these projects may or may not have existed with or without ASTRO 3D, but it's an attitude of collaboration that is fermented and grown in this room when people studying. So, with my final negative couple minutes left, I want to talk about how we can sort of plan this for the future, and how we can take that collaboration and set ourselves up for what's going on in the future. So we know SKA is coming. Square kilometer array is going to change a whole lot of people's science. And it's enough money, and the government is investing enough in this, that it's not enough for just the people who are doing, ASCAP science to keep doing that. We need to grow that into the entire community. And quite frankly, it's in your benefit. SKA is going to transform our ability to study cold gas or to study radio wavelength observations and many different galaxies. The problem is there's a huge activation energy of going from being an optical astronomer to being somebody who can do interferometric observations. So that's where we want to use this quality that we have made in the center of being cross-collaboration. And so the exec committee has agreed to sort of take special interest or special attention to anything you put in within the next year that will promote cross-node collaboration or cross-theme in a way that strengthens us towards SKA. What this will look like, workshops, I think I can come close to guaranteeing you're going to see some kind of workshop early next year that is something like blah, 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 radio optical, taking place somewhere. There you can go and you can learn and you can think about how this is going to fit into your project. You can start thinking, how can I use SKA? The other thing is bringing in international visitors, people who are working at SKA operations, cross-node support, maybe send your person out to Perth to have them sort of learn from a lot of the experts. The other thing is, in some ways, 40% of SKA is sitting out in South Africa right now. It's called Meerkat. Start using it now. So success here doesn't look like, we're not expecting to turn everyone into radio astronomers in the next 1.5 years. But success looks like beginning to build collaborations, beginning to build networks within the next year. More Meerkat proposals, that kind of stuff looks like success. All right, I think I'm way over time, yikes. All right, if you have more questions about this aspect, you can come talk to myself, you can talk to Kath Trott. Thank you.